Alright, so we're wrapping up our beginning of the week's work, and we're doing that by looking at this sort of intermediate point right at the mass equilibrium during this oscillation. So we've already gotten our mechanical energy at this bottom point, about 1.82 joules, and then our mechanical energy at that top point, about 1.84 joules. My guess as to why that discrepancy is there is that I just wasn't able to measure exactly precisely using this meter stick and just with my squinting at these distances, heights, displacements, all of those things. So in reality, and if I let this play a little bit, I can see all of these sort of individual energies fluctuating a lot. The elastic potential energy sometimes gets up really high, sometimes it'll go to zero. Same with this potential energy. Sometimes goes very high, sometimes goes pretty low. The kinetic energy at some points is zero and sometimes gets, like fairly high up there. But you don't see the same thing for this total energy, or this is our mechanical energy. So my guess is that these two numbers really should have been about the same, and I probably, if I were doing this properly, should have just left this at about 1.8 joules, because I really can't measure more precisely than that with the tools that I have in this simulation. So for our last bit of work today, we're going to apply conservation of mechanical energy to predict what that kinetic energy should be at that midpoint. But to do that, I'm going to pause the simulation right when the mass is at that midpoint. So I tried to get it, and I'm glad that I got it while the period trace was still there. Not at the bottom where we analyzed this on Monday, not at the top where we analyzed this yesterday on Tuesday's work, but today at this very midpoint. And so we are going to use the same three equations that we have all week. We've got our elastic potential energy one, which is 1/2 times k x squared. Again, for this 5-notch mass, or this 5-notch spring, excuse me, that spring constant is 7.84 newtons per meter. And then we just need to measure what this displacement is. So I'm going to use this meter stick, measure that green vector for our displacement, and it looks like it's about 20 centimeters. So I should make note of that. That's about 20 centimeters. And that's what I'm going to plug into this equation. Okay, so let's go ahead and do that calculation. So we've got 1/2, or 0.5 times 7.84 times 0.2 squared. Again, and that 0.2 is just this 20 centimeters converted into meters. I just moved the decimal twice to the left, or I divide by 100. Don't forget to square that displacement. 0.5 times 7.84 times 0.2 times 0.2. And that's 0.1568, or I'm going to write down here 0.16. So I'll round to the nearest 2 decimals just to stay consistent with what I've done elsewhere, even though I probably should just round this to 1 decimal point. Alright, so we've got our elastic potential energy. Now let's do the same thing that we've been doing to get our gravitational potential energy, which means we're going to need to measure a height, because our gravitational potential energy equation is 1/2 m, or excuse me, it's just mgh, mass times gravity times height. So I know the mass still. I know gravity on Earth is 9.8, but I don't yet know what that height is. Alright. So it looks to me, and I relined this meter stick up so that the bottom of it, or actually sort of the top of it, is on the ground at height equals 0. And then we measure up to this midpoint in the line. And that line, we actually could use this sort of movable line and put it there. It should be right on that mass equilibrium, though, so we can also measure to that black line. It looks to me like that sort of center of mass is right around 31 centimeters. So from 100 up to 31 centimeters, that is 69 centimeters. Or if I were converting that 2 meters. That is 0.69 meters. And so that's what we're going to plug in to this equation. So let's get that. For our mass, it's 150 grams here, but I know that that would just be 0.15 kilograms times 9.8 meters per second squared times 0.69 meters. Now let's see what we get when we plug that in, just multiplying all three of those things, all three of those measurements. And it's 1.0143, or I'm just going to write 1.01 joules. Okay, so we've gotten both our elastic and gravitational potential energies, and so the only one that we have left to calculate is our kinetic energy. Now, at the very top and bottom parts of this system, in that sort of pink and green parts of the simulation as I've drawn it over here, we made the same assumption, and that was that this object is at rest at those highest and lowest points, and we could confirm that by looking over at this energy graph and seeing that this green kinetic energy bar was basically at 0 at those 2 points. But that's not the case anymore. Kinetic energy is actually pretty big here. It's a lot bigger, it looks like, than our elastic potential energy. So we really can't make the same assumption at this midpoint that we could at those other two highs and lows in this system. So in order to calculate that, I ask you to apply conservation of mechanical energy. And to do that, we need to use our previous mechanical energies that we found. And maybe for this, I'm going to assume that for that mechanical energy to be conserved, our mechanical energy should be basically the same as those, or maybe I'll just do 1.83 joules or something, just right in between 1.82 and 1.84. I also could have made another assumption, maybe saying that they should both be about 1.8 if, like I said earlier, I should have just rounded to 1 decimal point, but for this, maybe I'll just leave it at 1.83, right between those two. And so that has to be equal to our sum of all of those other energies, right? So I take our 1.01 joule gravitational potential plus whatever our kinetic energy is, plus what we know our elastic potential energy is, and that should get us to this 1.83. And so if I'm going to solve for this kinetic energy, I need to subtract these two energies from both sides, and that'll get me whatever this missing kinetic energy is. So to get this kinetic energy, I'm doing in my calculator 1.83 for our total mechanical energy minus the pieces we know. So minus 1.01 minus 0.16, and it looks like that gets us a kinetic energy of 0.66 joules here at this midpoint. And that looks to me like that makes sense. That is in between the amount of elastic potential energy that we have. So this green bar is greater than that light blue bar for our elastic potential energy, but our kinetic energy is still significantly less than our gravitational potential energy, which is what this energy graph shows over here. So that lets me know that I think that we did this right.